Boa tarde, pessoal. Boa tarde a todos que nos acompanham. Então, vamos iniciar mais um seminário do Programa de Pós-Graduação em Física. E hoje a gente tem a satisfação de ter como seminarista o professor Gianpietro Cagnoli, da Universidade de Lyon. So, thank you, Gianpietro, for delivering this seminar to our physics department. It's a great pleasure for us to have you here. I mean, it would be even great if you could be here in person, but you know,
would be lovely. Yes.
Yeah, we manage this next year for sure. So okay. Gianpietro is a physics professor at the Université Claude Lyon. He worked on gravitational waves detector development since his master work 30 years ago. So his expertise is on the thermal noise problem and on the relaxation phenomena in amorphous materials. He have developed the first ever monolithic focused silica suspension, and he is now working on the optical coatings. He is head of the group GMAG, which is a member of the VIRGO-Collaboration for some time. So it's I mean, his work is some part is related to material science, and sometimes I tell people that it's really good to have a talk like this, because clearly show that materials are everywhere, even in they are key technologies for doing advancements in science, even in high energy physics. So Gianpietro, thank you very much for being here with us, and so it's up to you.
Okay, thank you very much, Antonio, for this great presentation. And I agree with you that material science is really important, because it solves a lot of problems within experiments that are really gigantic and very important to answer to the most fundamental question of humankind. So, and hopefully in my presentation, I will give you why the material science is important for gravitational wave detection. There is no other big experiment in the world that depends so much on material properties. And you will see why scientists doing solid-state physics are really important on this field that is entirely devoted to astronomy and astrophysics. So I'll start to share the screen. Hopefully the sound is fine. Okay, so close this. Okay, so hopefully you will see the screen and the starting of my presentation. So, so if there is any problem, is the moment to say it, because otherwise I will continue. Okay, so the title of my presentation is Gravitational Waves, and I will talk about the project that is called Einstein Telescope and the new generation of detectors that people on my field are eager to develop in the next 20, 30 years. So gravitational waves, you know, have been detected in the last 5 years. Okay, the first signal was detected in 2015. Okay, but probably after the first detection, the most astonishing event happened in 2017. Actually, there is a date that is August 17, 2017, was Thursday, and at 9:41 in the morning, and then after almost 2 seconds, an outburst of gamma rays was detected by the Fermi Observatory. So this is kind of remarkable because it never happened before that an event in space was detected by two different probes, completely different. One is an electromagnetic probe, almost particle probe, because gamma rays are the most energetic photons that you can have, and they go mostly like a particle. And the other probe is the gravitational one. So after a few hours, you see exactly at 2:55, the LIGO-Virgo detector, so collaboration, so putting together the signals from LIGO, the two LIGO in Virgo, were able to locate the direction of this gravitational wave signal with a precision of 28 square degree. And the position was located somewhere at the zenith of a point close to the Madagascar, as you can see on the image here of Earth. And also at the same time, we were able to estimate an approximately distance of 130 million of light years. So this is just a few hours after this detection. Then at that time, we are talking, sorry, this is a 1455, the local time in Europe. At that time, there were not any possible telescope available. But later, when the sun went down in the South America, so exactly at 8:33 in p.m. Fortaleza, the first telescope, the SWAP telescope, that is just a 1 meter diameter telescope in Las Campanas in Chile, detected what was the optical counterpart. Because with the localization given by the gravitational wave detection, the astronomers could have spotted just 50 galaxies that were in this region wide 28 square degrees and at a distance of 130 million light years. You'll see that in these two images of these galaxies, the NGC 4993, that's two photos taken, one in April and the other exactly in August the 17th, you can clearly see the appearance of a spot there, and this was identified as the source of the gamma ray burst, and most importantly, of gravitational wave detection. So the event was quite remarkable, not only because it was possible to associate an electromagnetic event to the gravitational wave one, but also it's because it was an event that was really close, so close that the astronomers could have taken the spectra for the following days. You will see in this image the spectra that is evolving in time. And for astronomers, these are like a gold mine, because in the spectrum, you will see what is around the event, this source of gravitational waves and gamma ray, and the astronomers are able to figure out what was the origin of the nature of this event. You will see here, for example, the first two lines are gravitational wave detection, gamma rays. Also, the event was observed in X-rays, ultraviolet, all the visible band, infrared, and also radio. Okay.
Gianpietro.
So, yes.
Gianpietro, sorry. Hello. Yeah, we are going to have some noisy on your sound. Could you please maybe, put off your camera, so maybe it will get better. So the.
Oh yes, okay.
It seems that the international connection has some instabilities. Let's try just sound.
Yes.
We hear you. Yeah.
Great. Okay, so let's see if it is right. Okay. And thank you for stopping me. So please do it as soon as something is not working properly. Thank you. So this event was probably the event that in the history of astronomy was more studied in so short time, but so many observatories and of different of all the electromagnetic spectrum. So this day in our community is quite remarkable. So it's a day so significant that now everybody remembers these days, because it's we said that this day was born a new science that is called Multi Messenger Astronomy. So the Multi Messenger is because we are using both the electromagnetic probe and the gravitational wave probe to study the single source. So now my presentation will be developed in 4 big chapters, as you can see here. I will tell you what is the situation at the moment about the collaboration, VIRGO and LIGO, and why we need another gravitational wave detector on Earth, and what are the technological scientific challenges that we have to face in order to build up underwent 3 data taking periods that are called observation periods. And the first 2 are here represented in these slides. So the first 01 started almost at the end of 2015. And it was characterized by the first detection of gravitational wave ever made. And the first period data taken lasted for just... Yes?
Yeah, sorry for interrupting you. I think I'm not sure if the screen is moving. I just have this view graph with 2 signals detected by Fermi Lab and LIGO. Maybe you move.
Yes.
And, oh, I'm sorry.
So
maybe you unshare and share again. Maybe that would work out.
Yeah. Okay.
Sorry.
Oh, okay. So I'll do it. So.
Oh yeah.
Okay. And then I'm going to share it again. I'm sorry about this. I mean,
no, yeah, it's,
the connection is.
Yeah, now I see the observation periods, O1 and
Okay, great, excellent, very good. So the two observation periods, O1 and O2, you see there's a little line that tells us the duration of each period, and when these two observation periods happened, okay? And as I said, the first period was characterized by the first detection of gravitational wave ever made, and the announcement of it was done on February 2016, 6 months after the signal was detected. This is because since this was the first detection, we needed to be really confident that we didn't do any mistake. So at the end of O1 and O2, 11 signals were detected, and 10 of them were coming from the merging of black holes binaries. And one of them was quite significant because was the detection of a neutron star merging. Okay, and it is exactly what I described to you a few minutes ago. So this is the signals, the totality of these 11 signals that were detected, represented in two ways. One is the time series of the signal here. So you see here the typical example of gravitational wave signal that is called chirp, because if you hear it, it is like a chirp of a bird. So it's a signal that is characterized by a frequency that is increasing. At the same time, the amplitude also is increasing at a point where the two objects are merging together and the signal stops. The other, on the background, you see what we call the omega scan. So it's a three-dimensional plot. On the x-axis, you have time. On the y-axis, you have frequency, okay? And the color, the intensity of color gives us the intensity of a signal. So you will see here also the chirp nature of gravitational wave signals, where when the time goes on, the frequency goes up, and also the intensity goes up to a point where the signal almost immediately disappears. Also, you see that there is a quite significant difference on the shape of the signal. Especially, for example, look at how different is the shape of a black hole merging, and here the shape of the signal coming from a neutron star merging. And all these kind of things will be explained later on, because it constitutes why gravitational waves are so powerful tool to study astronomical objects that are really peculiar, like black holes. So this is a movie that it represents the set of all these signal source that are made by black holes. You will see that we are detecting just the final life of these binaries when they are starting, when they are arriving to merge. So in the article that is called the catalog, here there is a table where for all the gravitational wave detection recorded.
Gianpietro, sorry.
Yes?
I think it's not a move in the view graph. So maybe let us do like this. You just put in your screen, but don't put in a presentation mode, because I think you are moving, but we are not seeing the slides changing. Yeah. Sorry.
So you do not see the movie?
No.
I'll try. Oh, I'm so I'll try to to do again the stop sharing, the sharing again, and I'll try to see if it works.
Yeah, now it's a. I guess if you leave in this in the other mode, maybe it would be good, because when you put in presentation mode, view graphs are not going. So yeah.
So if I leave the things in there like this.
Yeah, I think when you change, we see the change. Okay.
Okay.
Yeah.
So for example, now, do you see the movie?
No.
Okay, I'm sorry. Okay.
Yeah.
Well, I can send to you the presentation.
Yeah, but let's see this. Try to change the view graph. So just to see that we can see the view graph changing.
For example, now I changed the view graph. There is a table.
No, it's not changing the view graph. There is something that is not capturing the. Oh, okay. Now change. Yes, not change. Yes.
Okay.
Yeah.
So now you see the table. Yeah. Okay.
Yes.
So
right.
now I went back into the presentation mode.
Okay.
So the main purpose of this slides is just to tell you which kind of information we can derive from gravitational wave signals. You'll see that here we can measure the masses of the stars, of the black holes that are forming the binaries. Also, we can measure the spin of the two objects, and also we can measure the energy that was emitted in the process, and immediately also the distance at which the source is located, which is something that is like a dream for all the astronomers. Now I'm going to change slides. Let's see if you see it. Do you see the slide changed? It is called Evolution of Detectors Performance in O2.
Yes, Professor. We are seeing this slide, Evolution of Detectors Performance in O2.
Yeah. So here you can see how the detectors, the three detectors, Virgo and the two LIGO in Hanford, in Lewiston, performed. In the x-axis, you will see the weeks of data taking. And on the y-axis, you see what is called the binary neutron star range. So the distance at which the two detectors or any detectors is able to detect the signal coming from a binary of neutron stars. Okay, so the distance is given in megaparsec. Mega is million. Parsec is almost 3.2 light years. So if you want this distance converted in a million of light years, you just take the number, for example, 80, and you multiply by 3, and you have roughly the distance at which the detector is able to pick up a signal from the merging of neutron stars. And you will see that the detectors are not having the same performance all the time, but they evolved in time. Also, you will see on the y-axis some important, let's call it structure, that are located within at the distance that is indicated in the graph. For example, one that is most important for us is the Virgo cluster of galaxies that is located at almost 20 megaparsec. And when Virgo was designed as a detector that was able to see neutron stars coming from this kind of cluster of galaxies. This is why the detector is called Virgo. It's not an acronym, but just because it was designed to pick up the signal coming from this cluster that is made by 1,500 of galaxies, almost roughly. Okay. So there are many detectors in the world. There are 2 detectors in United States, and you see where they are located. 2 detectors in Europe. One is quite small, is GEO 600, which is in Germany. It's quite small with respect to the other. And there's now a 5th detector that is running at the moment, that is working in Japan. It is called Cagnoli. So all these detectors are sending their signals to a data center where the signals are compared and analyzed all together. And when the pipelines that are designed to detect a signal, they are triggered. Normally, when they are validated, after the validation, they are sent to the other astronomers, optical, radio astronomers, space telescopes, and so on, in order to see if there is a possible counterpart of the signals. So this is the way how now research in astronomy, part of the research in astronomy is done within this multi-messenger scheme. So in March this year, ended what is called observational period 3. We ended in 1 month before the deadline, the official deadline, because COVID struck severely Europe and United States. So we decided to stop the observation period. You will see there the length of this observation period. And if you go to this web page, you will see the totality of the 56 signals that have been detected in this period. Most of them are black holes, but there are several neutron stars binaries or neutron stars black hole binaries. So as you can see, there is an increment of signal detected. And this is because in the observation period 3, the performance of the detectors increased a lot. You will see here in this graph, that is the similar graph as we had seen before, that before the LIGO detectors were around 80 megaparsec as a black binary neutron stars range, and Virgo was just above 20. Now you'll see that in this observation period 3, that the detectors are able to see at much longer distance the signals. And definitely, if you pick up the signals that are coming from, that are weaker, because they are coming from places in the universe that is really far away, but in this case, you increment the volume of universe that is observed, and this is natural that you in the same period you can have more signals detected than before. So this is quite important in this kind of science to get to the signal that is smaller and smaller. And the way how to do it is only one, is to reduce the internal noise of the detectors. If you reduce the internal noise of the detectors, you're able to listen to signals that are weaker than before. And so you are able to observe a part of the universe that is every day bigger than before. So now you see that Virgo reached the Centaurus cluster that is about almost 3 times the original design of Virgo. This the detection range is given in binary neutron stars, but neutron stars are stars that are about 50% more massive than our sun. But if the signal are coming from black holes, normally the masses are much higher. So for black holes, you can expect a signal that is between 10 to 20 times larger than the signal coming from a neutron star's binary that is located at the same distance. So also it means that if the signal are coming from black holes, you can look at, you can detect events that are coming 10 to 20 times further away with respect to what you are able to do for neutron stars. And if some of you has some familiarity with cosmological distance, you can immediately see that the gravitational wave detectors are not detectors, local detectors. They're starting to have capabilities to detect really signals coming from a cosmological distance, like telescopes. So recently, when I said recently, is about a month ago, we published the results of the detection of one signal that is remarkable, because it tells us that the merging of these black holes happen with the black holes that have masses that are really, really high, 85 and 66 solar masses. These are black holes that cannot be produced by simple evolution of stars, unless the model of star evolution are completely wrong. So these are the origin of these black holes is still uncertain. Definitely could be originated from merging that happened billions of years before, but this chance is quite small. So you see also something that is remarkable is the distance at which
Professor, can you hear me?
so the redshift of this source is about 0.8. Yes?
Professor, the slide we are seeing is a noticeable detection during O3.
Yes, exactly.
Okay.
Yes, you see that I'm reading the table that is highlighted by the red highlight there, and
yes,
these are
in the table. We can see.
Exactly.
I'm sorry to interrupt you. Okay.
No, it's fine. You have done well. So this is as I said, this is kind of remarkable because the masses of the black holes are really gigantic, and also you will see that there's something happened here, which is happens always when you have the merging of black holes. You have to imagine that black holes are, when they are merging, they are almost going at the speed of light. So, and immediately all the kinetic energy should be almost reduced to zero. And we will see that in the mass reduction. So before the merging, the mass of the binary was 150 solar mass, and after the merging is only 142. So it means that a total of 8 solar masses disappeared from the system, and this enormous energy was emitted on the gravitational on the space-time fabric of the space-time as a form of gravitational wave. So this gigantic, energetic gigantic wave was emitted by this this source, and this wave propagates for billions and billions of years before being detected on Earth. So this is was the most luminous events ever detected by humankind so far. The luminosity of this event, luminosity in terms of power emitted at the maximum, is several times the luminosity of all the stars of the universe. Just to give you the how much is the energy, the power of this event. So big projects are made by large collaboration. You will see here in this graph that is called this slides that is called the VIRGO-Collaboration. All the groups that are making Virgo, there are several, and in red is the location of the Virgo detector. There are several countries now contributing to the science of Virgo, 500 members, and the members are divided in three kinds of scientists. In the first group where I belong to is what they are called the detector developers. So the people that are developing all the different parts of the detectors. So we are doing optics, laser, mechanics, we develop materials and do electronics and so on. And another group of people are the detector operators. These are the people that are quite important because they maintain in an efficient way the machine. And also the third group are the data analysts that have the responsibility to work up the signals and to study the astrophysical implication of their findings. So unfortunately, this is in French, but you will see here all the different kind of expertise the gravitational wave detection or detector need to create. So on the right, you have just the theoretical one, the astrophysics and the detection of signals. And then continuing, you have all this other experimental expertise like optics, lasers, and then you will see that we need material scientists and expert of condensed matter and so on. So Virgo is not the only collaboration. There is the LIGO collaboration that is much bigger than Virgo. So there are 18 countries, and Virgo is constituted. LIGO is constituted by 1,300 scientists roughly, and only 700 people are signing the papers of the collaboration. You will see there that also in Brazil there are two groups that are working in LIGO. The first group, I hope you see the transparency, the slides. The first group is in Natal, and Ricardo Sturani is the head of the group. He works at the International Institute of Physics, and his group is yes.
Yeah, I think we are still in the old view graph. So maybe you are showing the map now, but we are not seeing the map.
Oh gosh,
I don't know why.
So
anyway.
You do not see the LIGO collaboration?
No. It's a noticeable
Okay.
detection during O3. Yeah.
Okay, so I'll do the same trick.
Yeah.
So I'll stop it. Share the screen. So now you see the...
Yeah, now yeah.
Yeah, okay, great access. So this is the LIGO collaboration, the two groups in Brazil. So the first group that I want to present is the groups of Professor Riccardo Sturani. And he works on signal detection, but also most importantly on the astrophysical implication of the parameters that are found in gravitational waves. The second group is the Institute of ENPE, and this is a group that is developing the detector, and there is a detector in Brazil that is made by using a different kind of technology that is called the technology of the resonant masses. Okay, and this is a group that historically developed this kind of detectors, and it's quite interesting. So I said that there is a network of detectors. I hope that you see the slides now. That is called a network of detectors. So we have two LIGO detectors at the state of Washington and Louisiana. And then we have Virgo in Italy. And the fourth detector is Kagra in Japan, that is underground. And this will represent the future of gravitational wave detection, as you will see. So at the moment, the detectors are undergoing important upgrades. So the first you will see here for Virgo, the first Virgo ended in 2017. Between 2012 and 2023, it is called what is called the second generation of Virgo. That is called also advanced Virgo, and this is the significant upgrade that Virgo did, and that with that upgrade, the Virgo was able to detect the gravitational wave signals, and now we are in the development of a third upgrade called Advanced Virgo Plus. So in this graph, you will see the spectrum of noise of the detector at the moment. So here in this plot on the x-axis, you see the frequency, and on the y-axis, you see the amplitude spectral density of the noise given in amplitude of gravitational waves. You will see that there is a minima around 100 Hertz. This is where the detector is most sensitive, because the noise is the lowest. So in the upgrades, we want to reduce even further this noise that is produced inside the detectors. You will see what we're going to expect at the end of this upgrade. So this is concludes the part of what is the status of the detectors. So now, why we need a completely new generation of detectors? What's happening that is in these detectors are not working? So in order to explain why we need a different kind of detectors, I need to say 2 or 3 things about the polarization of gravitational waves. As you have seen before, so I hope that you will see this slides that is called 2 or 3 things to know on gravitational wave polarization.
Yes,
in this slides, it is represented a binary of black holes, as you can see there at the top. And we are going to see the emission of gravitational wave in the plane of the binary, okay? So now there is an animation that I hope it works. Do you see the animation of a gravitational wave, or you do not see anything?
No, Professor. Right now we are not seeing them.
Okay. I'll try to to see if I do it again, the same trick. I hope that it works. So now you should see the. Do you see the animation?
No, Professor. Unfortunately, we are not seeing.
You see just a black rectangular.
Now it's starting an image, but it's still. It's not moving.
Okay. Okay, I understand. So I stop the, no, this is not the right moment.
Professor, can you hear me?
Do you see it?
We still, to me, it looks like the image, the animation is not it's not happening. It looks like oh,
at least
sorry.
the image is still, yes, it's still the image.
Yes.
Not moving. At least you see something. Yeah. Okay. So, well, this is kind of tricky because it was kind of nice. The well, I'll give you the basic idea.
It's like the image is going frame by frame.
Yes.
It's not fluid.
Okay. Yeah. So I'll tell you what is the main message of this two slides that are going on. So in this first slide, when you pick up the signal from a direction that is parallel to the orbital plane, the polarization of gravitational wave is linear. Okay. Some of you maybe have done the electromagnetic waves, and those are familiar with the concept of polarization. So the gravitational wave emission along the plane is linear, okay? Whereas if we go to if we pick up the signal that is coming from a direction that is perfectly orthogonal to the plane, and I hope now the transparency has changed, because now in the title you should read the circular. So when you pick up the signal that coming from the direction that is orthogonal to the orbital plane, the signal, gravitational wave signal, is circularly polarized. Okay, so this is the main message. Unfortunately, with a gravitational wave detector, with any gravitational wave detector that is working at the moment, it's not possible to pick up the two polarization. With one detector, we are able to pick up just one of the two polarization. So we will never see the other polarization. So we will never understand what is the inclination of the orbits of the binary. Because this is something that is quite unique of gravitational waves. That's looking at the two polarization, we are able to measure the inclination of the orbits of the binary, even if the objects are on the other side of the universe. So, and now probably this is one of the most important slides of my presentation. So what we can learn simply looking at the signal of gravitational waves. So the slides is called the binary parameters hidden in gravitational wave signals. And see here you can see on the left represented a binary of black holes with the orbital plane with a certain inclination, okay? And then it is represented here typical gravitational wave signals. So first parameter that we can immediately read from the signal is the frequency. The frequency of the gravitational wave is exactly double of the frequency of the orbit, the orbital frequency. So if you want to measure the orbital frequency of the binary, you have to pick up the instantaneous frequency of the wave and divide it by 2. Okay. Second parameter that is quite important, as I said, if we were able to pick up the two polarization of gravitational waves, the two polarization are labeled plus and X and cross, sorry, plus and cross. Making the ratio of the two is possible to work out what is the inclination of the orbital plane. But unfortunately, none of the detectors is able to detect the polarization. Then, looking at measuring the amplitude of gravitational wave, we are able to work out the distance. This is because the amplitude of gravitational waves depends on the frequency, the two masses, definitely the distance, and the inclination of the orbital plane. So frequency is measured. The inclination at some point it will be measured. Then, in order to work out the distance, we should know the masses. Okay, and this is the expression of the amplitude of gravitational waves in one of the simplest model possible that we have. So the masses are determined in a kind of strange combination, which is called the chirp mass. And the masses are, the chirp mass can be detected if we not only measure the frequency of the signal, but also the rate at which the frequency is changing. You will see here in the last equation that I put there, that if we measure, if we make the ratio between the rate of change of frequency and the frequency at the 11th power, so we are able to work out what is this chirp mass. So the it's quite astonishing that with this measurement of these simple parameters, we're able to measure the masses of the system, the distance, the orbital inclination of the sources that are located everywhere in the universe. Unfortunately, I have to apologize with two people that are developed, they spend their life on making models more and more difficult in order really to dig out as many parameters as possible from the source. I made just a simple cartoon image of what in reality is much more complicated, but I hope I gave you the essence of why it is important to what is the information contained in gravitational wave signals. So then, why we need another kind of detectors? Well, first, we need a higher signal-to-noise ratio. The signal-to-noise ratio depends on how big the detector is. So at the moment, Virgo and LIGO have a size of 3 and 4 kilometers. But here we are talking of detectors that are arm length of interferometers of 10 to 40 kilometers. And also, in order to reduce the internal noises, what we have to do is to reduce the cryogenic temperature and also possibly to locate the detectors underground. We need another kind of network generation of detectors because we need two polarization to be detected at the same time. So we need to have at least 2 interferometers located at the same place. We need to make the detection bandwidth the largest as possible in order to be able to detect a signal coming from different kind of sources. And this is the reason why what is called the Einstein Telescope, which is the project, the European project that we are trying to build up, is divided in 2 types of detectors, the high frequency and the low frequency of detectors. So in reality, what this project Einstein Telescope will be, it will be a multi-interferometer detector. Some of these interferometers are working at cryogenic temperatures, some others at room temperature. And also, we need another detectors because the infrastructure of the existing detectors start to be give some problems about vacuum, and really the structure is deteriorating really fast. So this new project, the Einstein Telescope, will have an internal noise of that sort, of that magnitude, as compared to the existing detectors. You will see what does it mean to have a reduction of 10 times of the internal noise, and the bandwidth is also much bigger than the existing detectors. So there will be plenty of subjects specific to gravitational waves that are important to investigate. Some of them are done at the same time, what is called the high energy particle physics, and it will be really incredible that one day we are going to compare the result obtained by gravitational waves with the result obtained in using particle accelerator or cosmic rays, or doing simply cosmology with the normal telescope. Okay, and we'll see here, we do not have time to go over all these questions, but you'll see that are quite important questions in modern science that still the answer is pending. So there is a science book that you can download on the internet that will tell you all the fantastic things that can be done with this new kind of detectors. I listed here a few of them. For example, a very important thing is to provide a measurement of or a test of the equation of state of a neutron star, because apparently there are many parameters that are not clear yet, and gravitational waves are able, looking just at the signals of a merging of neutron stars, the gravitational wave are able to make a difference between the different models. Now I'm on slide 36. I don't know if this is the case for you. At the bottom right, you should see slide 36.
Yes, Professor.
Okay, So Einstein Telescope, it will be so powerful that will detect any signal, any gravitational signal coming from the visible universe. So we are going to detect merging of black holes from region of the universe that are called the dark age. So before the formation of any stars in the universe, scientists are saying that there are that moment there are also the black holes that are coming from the origin of the universe. And if there is any merging of these black holes, the Einstein Telescope will be able to pick up them. Then there is test of general relativity at higher field, and I'll skip this because I want to go here, which is the third part that will tell us why material science is really fundamental for the detection of gravitational waves. So which are the challenges that we have to face? Well, first, is an engineering challenge that we have to face, because we have to excavate 30 kilometers of tunnel underground, 200 meters, in order to place the detectors underground in order to reduce one of the most important noise of the detectors. Then there is another challenge that is still regarding engineering, is to provide all the vacuum pipe and equipments that are necessary to run the detector. For each tunnel, we have 6 high vacuum pipes that have to run for the 10 kilometers of the tunnel. And the engineering work is so important that the cost of the detectors, 2/3 of the cost of the detectors is coming from the engineering part, so excavation and vacuum pipes. So, as I said, the detectors are interferometers, and you will see that they are in a triangular shape. There are 3 interferometers, 3 interferometers at high temperature and 3 interferometers at cryogenic temperatures. The cryogenic one are also the detectors that will pick up the signal at the lowest frequency as possible. The high temperature, so the room temperature interferometers, are instead concentrating the detection at high frequency. So you will see here that this new type of detectors is made by tens of optics, and you will see now why the engineering part is kind of important, because this tunnels and caverns will be packed of vacuum tools and pipes and tanks. So there are several other challenges. So the engineering challenges, we have seen it. We have to build up the cryogenics for all these detectors, and there will be the need to develop new materials in optics, as we can see in a few minutes. New lasers, mechanics is very important. We need to develop quantum tools to reduce the internal noise of the detectors, and so on. Okay, now let's see something that is really important for those who are studying condensed matter physics, because I will present you the most important noise that at the moment is limiting the detectors, where the detectors are more sensitive. You will see here a typical gravitational wave detectors. They are made by two Fabry-Perot cavities. Here you will see here the cavity, the vertical cavity, so the north cavity and the east cavity, because the detectors is parallel to the ground. And the gravitational waves are detected because when a wave is passing through the detector, the distance between the length of the two Fabry-Perot cavities is changing in opposite phase. So therefore, when the light that is recombined here at the beam splitter is changing the interference, and this change of the intensity is picked up by the photodiodes that is at the output of the interferometer. Well, now, since the detection is made because the length of the Fabry-Perot cavities is changing, you immediately you see that if there is any other mechanism that is able to change the length of Fabry-Perot cavity, but is not related to gravitational wave, is producing the same kind of signal, that it might be able to hide the true gravitational wave signal. So one of the possibility of the noises that are making the length of the cavity changing is the fact that the shape of the mirrors is fluctuating in time in a random way. And this is called thermal noise. Any object fluctuates, has its shape that fluctuates in time randomly. And this is because there is a random fluctuation of temperature inside the material, and also because materials unfortunately, they have defects, and the atoms are randomly deciding to change their position because of these defects. Now, if you operate the detector at room temperature, the best material that humankind has found is fused silica, which is a glass. Fused silica is the material that has the lowest thermal noise on the universe, for what we know. And it would be better not to use any crystals, because crystals normally have thermal expansion that is significantly higher than glasses. So any thermal fluctuations inside the crystals produces corresponding fluctuations in the shape of the material, of the solid, which is really bad. On the contrary, when we operate the detector at cryogenic temperatures, glasses are becoming really bad, because normally the fluctuations of the relaxation that characterize glasses are becoming more and more important at cryogenic temperature, or better saying, the fluctuation of shape of glasses at room temperature belongs to the gigahertz region, whereas when you decrease the temperature, these fluctuations are becoming having a characteristic frequency that is comparable to that of gravitational waves. So they're really bad. So in this case, at cryogenic temperature, you need to replace all the, if it's possible, all the material in optics with crystals, okay? Especially substrate are quite important. So at room temperature, fused silica substrate is what you have to use. When you decrease the temperature, you have to go to silicon or to sapphire. So here in this slides, that is called the origin of thermal noise in the optical coatings, you will see why there is thermal noise. I already introduced you with the reason. Here there is a more pictorial representation of thermal noise. So the mirrors on gravitational waves are made by a substrate that I told you is infused silica, and the reflecting surface is not made by a metal, because any metals can absorb the 1 or 2% of the light. So therefore, people have developed what is called the Bragg reflector. So the reflection of light is made by the position of several layers of two different glasses, different in refractive index. And so each boundaries between two layers is producing a reflecting wave. And if we're able to control the thickness of each of this layer, all the reflections are making interference, a positive interference. And so at the end, we have a really large reflection from this, what is called stack of coating layers. And so we realize what is called a Bragg reflector, okay? So now, as any other, So as any other amorphous material, also the layer of these coating stacks are subjected to change in the atomic position of the molecules that are constituting the glass. Here, on the left side, you will see the atypical structure of silica that is made of a tetragon here, where the silicon atom is at the center, and then you have 4 oxygen atoms at the edge. You will see here, because the structure is amorphous, there is a lot of equilibrium position that the structure cannot obtain. So therefore, driven by thermal agitation, the structure can change the equilibrium position. So here on the graph, you will see that this is just simulation. If we take, for example, one of these oxygen atoms and we monitor the position X, Y, and Z, we will see that now and then the equilibrium position of this oxygen atom is changing, okay? And this sudden change of equilibrium position is what is determining the thermal noise. So thermal noise is determined by this fluctuation of the equilibrium position, which, if you think carefully, is exactly what I told you before. Practically, the shape of the object at the molecular level is changing. So we need to develop different kind of material. We need to understand how to reduce this this relaxation mechanism inside the amorphous material. Or if we change temperature, for example, we need to leave out any amorphous material and concentrate our research on crystalline materials. Here we have 2 examples of possible materials, sapphire and silicon, and they have different pros and cons, the 2 materials. Here in Lyon, I'm the PI of a project called OSAG, which stands for Sapphire Optics for Gravitational Astronomy in French, okay? And this project is already funded, and we are going to develop a massive oven, really a gigantic oven, that will be able to produce sapphire ingots of a mass of 500 kilograms. So these ingots have a diameter of almost 50 centimeters, for a total length of 60 centimeters. And the total weight, as I said, is half ton. The ingots are produced in the Chiropoulos way, which is sketched here on the right. So we in a crucible we are going to melt at more than 2,000 degrees centigrade the half ton of alumina, which is the oxide of aluminum that is at the basis of pure sapphire. And then we put what is called a germ, which is a seed, which will give to the crystal, to the ingots, the right crystal orientation. And when the seed will touch the surface of the liquid, we're going to slowly decrease the temperature. A colleague of mine, which is expert in this technique, said that we're going to take 40 days to cool down this mass slowly in order to produce half ton of sapphire. So it would be really interesting to see this process terminated. So now we go to the final part of the presentation, which is a short vision of the future. This will be really short. So when all this project will happen, you will see here that we are almost at the end of 2020. So we think that if the project, the Einstein Telescope project, will be approved, the construction will happen in about 6 or 7 years. Okay, but we think that the operation of the detectors will be after 2032, maybe 2035. Okay, so this is a kind of project that younger scientists are very welcome to start, because my generation will not see the results of this kind of detectors. So you, the young people, will exploit this new type of detectors. So what will be the future? Well, in United States as well as Europe are thinking to develop a gigantic detector, very similar to Einstein Telescope. And so in the future, we'll have 3 detectors in the United States, 2 detectors in Europe, 1 in India, and a larger detectors, or an upgraded version of the Japanese detectors. Also, at the same time, scientists are collaborating to send in space a mission which is called LISA, that is able to detect the gravitational waves from space. So in that, as I said before, we will be able to detect any merging of black holes from the all visible universe. In this plot, you will see that, for example, the telescopes, here is represented the Space Telescope at left. The most distant galaxy, the further galaxy ever seen by Hubble, was a galaxy with a redshift equal to 11. Well, we are going to detect with the Einstein Telescope signals coming from region of universe characterized by a redshift of 70, which is quite remarkable. At that distance, no stars were formed, so for that reason, it's called the cosmic dark ages, because no visible light was shown in the universe at that epoch. But we believe that there are black holes produced during the Big Bang. So there's a final remark on the fact that maybe I anticipated a question. Why build up a detector on Earth when there will be a detector on space called LISA? Because LISA, as you can see here in this plot, will detect gravitational wave from 10 to the minus 4 to 10 to the minus 1 hertz. That is a band that is completely impossible for Earth-based detectors, as you can see here at the bottom right. On the contrary, for space detectors, it will be really difficult to detect signal at high frequency because the signals are becoming really, really small. Okay, so and they should operate a detector that is very much similar to the one based on Earth. So scientists wisely have decided to play the game of complementarity. So LISA will detect signals that are belonging to very massive black holes, or black holes that are merging, they will merge in years, and they leave the detection band of LISA, and they will enter the detection band of Einstein Telescope and the other Earth-based detectors. So there's a publicity for the young people. So Mr. Einstein wants you because he developed this theory more than 100 years ago, and there is still a lot to discover on that field. And as I can briefly show you, to enter in this amazing world of astrophysics, you can play very, very well the card of scientists on materials, because only developments on materials will be able to open up the possibility for this new detectors and new science. Thank you for your attention. So that's it.
Yeah, okay. Thank you, Gianpietro, for the talk. Actually, I have one question for you. It's amazing how the limit of observing the universe is being pushed by these new detectors. So, but my question is related to materials, to material science, actually. I mean,
Yeah.
I guess the flatness of these mirrors should be very critical regarding the detection of the signal. So maybe as a bigger technological issue, maybe you cannot unveil it, but how do you get the flatness of such a big mirror? It's just during the growth process, or you need some post-processing?
Yeah. Is a post process. Either the amorphous version, the fused silica, or the sapphire mirror here. The first things to do is to cut the material. Okay, you have to cut the material, and like you can see here on this picture, upper left. Then you have to give it to the companies that are expert of polishing it. And the first things is to polish mechanically with the grinding tools. And then the last step that is done only on the surface that will reflect light, you will do the ion beam polishing. So you're going to send argon atoms that are ablating the surface, and they are able to provide you with a surface corrected to the angstrom level on diameter that are going up to 40, 50 centimeters. And at the moment, there are not so many companies that are able to do it. There's the best company that does the job is an American company called Zygo, and that's it. So once you prepare the substrate in this way, you have to deposit the coatings in order to reflect light. This is completely another kind of job. You will not obtain the same precision in the shape, but the laboratory where I was working here in Lyon was able to have a precision of 3 nanometers on 20 centimeter diameter of coatings, which is remarkable because the technique is kind of old, is ion beam sputtering. You sputter the material that you want to deposit with argon atom, and you produce a plume, okay? And you need to use masks to cover the mirror in order to guarantee the thickness uniformity.
Okay. If you can, you can turn on your camera again. Yes, I
Okay.
got I got another question here. Is regarding laser technology, could you comment a little bit on kind of new technology?
Yeah.
You mean about the lasers? Is in
Yes.
time, in power? What else?
So the lasers so far, there is one only type of laser developed that is guaranteeing the quality in terms of frequency noise. This is the YAG laser. So all the interferometers are working at 1064 nanometers. And normally these lasers have amplifiers that are able to push up the power up to 200 watts. But none of the detectors is using such higher power yet. The highest power out of the laser system is about 50-60 watts at the moment. Inside the cavity, we are having about 100 kilowatts of laser power, because the light will be stored in the fabric cavity.
Yeah. So we have one question for you on the screen.
Yes. With improvements of equipment by 2028, which of the parameter, orbital frequency, inclination, distance, etc., is expected to be measured more accurately? One of the things that we like most to improve a lot is the accuracy in the distance. So therefore, we are going to we hope to detect the two polarization. This is the third generation of detectors. So by in the next upgrade, we will not be able to do it. But still, we're going to lower the internal noise of the detectors. So we're going to have a better estimate of the masses of the system. And we are going to detect what is called the ring down. So when the two black holes are merging, the black hole that is formed is ringing down. And there is a lot of things that we can learn from that dynamics. In the third generation of detectors, the going down with frequency also, it's very important, because we are able to pick up signal coming from massive black holes. And also when we go to very far distances, the redshift is called redshift because it's lowering the frequency. So a binary that is redshift equal to 1 has a frequency that is half the real one of the source, just because the distance, just because the cosmological expansion is making the frequency lower and lower, the further away is the source.
Okay. Let me ask another question. Maybe, I mean, it's not my field, but I was just guessing, like fluctuations and attenuation of vibration is a key issue for those detectors, right? I mean, it's
Yeah.
It seems that
Yes.
It's almost overcoming these barriers. But could you comment if there is some ideas being developed for putting like a kind of different detectors, of course, but like in some in space, not in Earth?
Yes. The detectors on space, definitely they should not have any seismic noise problem. But they have a different kind of problems because well, the main problem is that you put the system there and you have to invent a system that is able to turn on by human operation on Earth, and everything should be guaranteed. So at the moment, it's almost impossible to have a detector that is really an interferometer on space, because the sensitivity is so high that you need to put your hands a lot on the interferometer in order to complete what is called the commissioning of the detectors that should put the detector at the right level of noise. So you have to continuously working to push down the noise. In fact, the space detectors are kind of different completely. Although they're using mirrors, they're using lasers, but they are based on a completely different kind of detection. You cannot do any interferometry with them. Mm-hmm. Because in order to increase the gravitational wave signal, so to increase this displacement, this length variation, the starting length of the mirrors should be millions of kilometers. The original project is based on the idea to have mirrors to monitor distance on a base of 5 millions of kilometers. So with 5 millions of kilometers, when gravitational wave is passing, the effect is to producing a displacement of picometers, which is gigantic in our field. A picometer in 5 millions of kilometers is small, but a picometer can be detected much easier than the displacement that you have to detect on Earth when the base is only 3 kilometers. So in that case, what is the problem? Is in 5 millions of kilometers, you cannot do interferometry because the beam, the laser beam, diverges so much after 5 millions of kilometers that the spots becomes 200 kilometers wide. So no interferometry, but what you have to do is to measure the time of flight of light, making the phase comparison between a local oscillator and the light that you receive from the other spacecraft. You can measure the time of flight and the time of flight variation, which is the effect of gravitational waves. Not the time of flight per se, but the time of flight variation. So therefore, you have to completely change the scheme. So no interferometry, but a phase comparison. Thermal noise is not a problem because at picometer level, the thermal noise is much lower. So you do not have any thermal noise. Definitely, you have you solve the problem of seismic noise because there is no seismic noise. Although you need to go very far away from Earth because you are sensitive to any slow motion, slow variation of the gravitational field. So you need to go really far away and not to be perturbed by motion of oceans and seismic motion of Earth and this kind of things. Because you see, you have to pick up signals that have a millihertz frequency, so a 20 minutes period. So it's a different kind of physics and different kind of detectors.
Okay. Oh, that's amazing. Yeah. So yeah, it seems that I do not have any more questions. So yeah. So thank you very much for your time, for taking your time, and for delivering.
Sorry for the problems, for technical problems.
Yeah, but it's I mean, it's okay. It's sometimes happens, sometimes goes like smoothly, but sometimes happens. But it's fine. So it's part of this new way of discussing and having talks. So thank you very much for your talk, and we appreciate that very, very, very much. I hope we see.
It was a pleasure for me.
Yeah,
An honor.
Yeah, I hope to see you soon, either in Lyon or here. Okay.
Yes, yes, definitely. We have contacts, mutual contacts that can facilitate this.
Right.
Great.
So, yeah.
Thank you very much.
Have a good evening. Yeah.
You too. Thank you very much. Bye.
Bye.